Hey everyone, Ahmed here. Space is a fascinating thing. It's quite mysterious, and today I'm going to talk about 5 things that you should know about space. So let's begin. Stars have an age. The age of a star depends on its size. It is thought that a star with the same mass of our Sun may stay for as long as 10 billion years. Simply put, stars form from the accumulation of gas and dust. And when a star is formed by the work of gravity, hydrogen is converted into helium in a process known as nuclear fusion. The more massive the star is, the faster it will consume its energy. But what happens when it does? There is something known as a supernova, which is a bright explosion that results from a massive star's core collapsing while running out of energy. Not all stars produce a supernova, as this is determined by the mass of the star.
Stars like our Sun could become what's known as a white dwarf, and stars much more massive than our Sun could explode as a supernova and form a neutron star or even a black hole.
A massive star known as Betelgeuse, which is the 10th brightest star in the visible night sky, has been observed, and based on changes in the star's brightness, it is suggested that this may be an indication that the star is in its final stages and that it could perhaps explode within the next 100,000 years. If it does, from Earth, Betelgeuse would shine bright for a while. It may even be nearly as bright as the full moon in the night sky. It would be a phenomenal view. However, the star's change in luminosity could be attributable to extinction, meaning that the observed changes in the star's brightness could be due to the presence of dust along the line of sight of the observation. We also don't know much about how a star would behave in its final stages, so it remains a speculation. But that may change. Since light takes time to reach Earth, if Betelgeuse does explode, however, we won't know about it until light from the event reaches Earth, which takes a long time, a really long time. Which brings us to the next point. Light takes time to travel. The speed of light is 300,000 kilometers per second. Here on Earth, everything we see happening is instantaneous, but for really distant objects in space, it's different. The average distance of the Sun from Earth is 150 million kilometers. I say average because of Earth's elliptical orbit around the Sun. So light from the Sun, on average, takes about 8.3 minutes to reach Earth. That is 8 minutes and 18 seconds. Meaning we see the Sun as it was 8 minutes ago. Now this may not be a big deal, but when it comes to stars and galaxies that are millions of light years away from us, our observations of these galaxies do not reflect how they are now, but rather how they were millions of years ago. Normal images of our solar system depict planets closer than they are in reality, but how far are we talking about? To start, let's look at our moon. The moon is, on average, 384,400 kilometers away from Earth, and most images depict the moon and Earth that close to each other. But in reality, the moon is closer to being this far from Earth. But how about planets in our solar system? Well, it's quite difficult to illustrate in images, let alone to scale, but you can visit omgspace.net, which attempts to simulate the distance. Launched in August of 1977, it took Voyager 2 space probe 12 years to reach Neptune, which is the farthest planet in our solar system. A technique known as gravity assist was used, which in simple terms takes advantage of the gravity of planets to increase the velocity and change the trajectory of the spacecraft to escape the Sun's gravity, which also enables it to reach interstellar space. But what's the size of our solar system? It's worth noting that the end of the solar system may vary depending on how you define it. Let me explain. The AU, short for astronomical unit, is a unit of measurement used for distances. It's equal to the average distance between the Sun and Earth. As defined in 2012, 1 AU is equal to 149,597,870,700 meters. If we say that the solar system ends with the farthest known planet, i.e. Neptune, we're looking at a radius of around 30 astronomical units and a diameter of around 60. Or we could use the Sun's influence as a way to define the diameter of the solar system. The Sun releases solar wind, a bubble comprised of charged particles that extend far beyond the known planets, called the heliosphere. We could use the heliosphere to define the edge of the solar system. Measurements by Voyager 1 indicate that it crossed the termination shock, which is where the solar wind particles slow down to a subsonic speed with a distance of 94 astronomical units from the Sun, and at a different direction, measurements by Voyager 2 were at 84 astronomical units. Voyager 1 became the first spacecraft to go beyond the heliopause at about 122 astronomical units from the Sun. That is 18 billion kilometers. The heliopause is thought to be the limit of the solar wind, the outer edge in which the interstellar medium stops the solar wind. If we use that as the radius, we're looking at a diameter of around 244 astronomical units. Discovered by and named after the Dutch astronomer Jan Oort, the Oort cloud is the most distant region in the solar system. It's basically a sphere of icy objects, and the outer edge of the Oort cloud is thought to be between 10,000 and 100,000 astronomical units. So using the Oort cloud to define the edge of the solar system, we're looking at a diameter of anywhere between 20,000 and 200,000 astronomical units. So it should be clear at this point that in order to estimate the size of the solar system, we have to define where it ends. Space is a harsh environment, to say the least. Extreme temperatures, low pressure, and radiation represent a challenge for us humans when we try to explore it. Let's briefly go through that. First, let's talk about sound. Space is silent because there is no medium for sound to travel in. Sound waves can travel through solid, liquid, or gas mediums by vibration, but space lacks that medium. However, space isn't really a perfect vacuum. It's close, but it's not really empty. It contains very little bits of matter, dust, and gas atoms, and there can be really rare areas in space where sound can actually occur, but it's certainly not audible at all. In 2003, at NASA's Chandra X-ray Observatory, astronomers detected sound waves coming from a black hole in the Perseus cluster. But in no way this sound can be heard. In fact, it's considered the lowest sound wave that has ever been detected by humans from an object in the universe. Since the Sun is the source of heat for the solar system, temperatures in outer space can either be extremely low or extremely high depending on whether an object is facing the Sun or not. Since our moon doesn't have an atmosphere, during sunlight, temperatures there can reach 127 degrees Celsius and minus 173 degrees when it's not facing the Sun. Cold is the absence of heat, and since there is no air in space, conduction and convection do not occur to transfer heat. It's only transferred via radiation, and therefore it takes a while for an object to lose heat in deep space. The coldest place currently known in the universe is the Boomerang Nebula, about 5,000 light-years away from Earth, measured at just 1 Kelvin. For perspective, water freezes at 273 Kelvin. As for pressure, well, it's pretty much absent. On Earth, temperature and pressure change with altitude, but obviously the human body can't survive the absence of pressure in outer space without a spacesuit. When talking about space radiation, we're referring to galactic cosmic rays, trapped radiation, i.e. radiation trapped by Earth's magnetic field, and solar particle events. They all represent ionizing radiation. This radiation may highly affect astronauts and puts them at risk for cancer, radiation sickness, degenerative diseases, and central nervous system effects. Gravity is the force of attraction between all matter in the universe. It obviously plays an important role in the evolution of the universe, but it's actually the weakest known natural force. Gravity doesn't just affect matter, it also affects light. There's something called gravitational lensing, which is what happens when light from distant galaxies is bent as it passes through massive objects in space. But where does gravity come from? There's a hypothesis that gravity is actually mediated by particles called gravitons, but that's just unproven and remains a hypothesis. According to the general theory of relativity, thanks to this guy, gravity is a result of space-time curvature, as shown here. meaning that any object with mass bends both space and time, which causes other objects with smaller mass to be drawn to it. Now the problem is that there is a contradiction between the general theory of relativity and quantum mechanics. With relativity, events are deterministic, while with quantum mechanics, it's a matter of probability and uncertainty. On the one hand, relativity can't account for gravity on a particle scale. On the other hand, a theory of quantum gravity is needed to describe gravity in accordance with quantum mechanics, and unfortunately, we just don't have it yet. To elaborate further, we have four known fundamental forces in nature: electromagnetism, gravitation, the weak force, and the strong force. Gravity is accounted for with the theory of relativity, and it even predicted the existence of black holes, the regions in space where gray matter is condensed into a really tiny area, and gravity is so strong that not even light can escape. It's thought that black holes can form when a really massive star dies and collapses. The other three forces that I mentioned are described with quantum mechanics and quantum field theory. The problem between general relativity and quantum mechanics remains. But here is a fascinating thing. Did you know that all matter in the universe that we have observed is thought to only make up about 5% of the universe? The rest of the universe is made up of about 27% dark matter and about 68% dark energy. Dark matter is a form of matter that, well, that's it. We know that it exists, but we have absolutely no clue what it is. So based on the shape of galaxies, their rotation speed, and the observable matter in them, there's just not enough matter with enough gravity to hold them together. There must be something else, something that allows galaxies to be held together: dark matter. However, we know more about what dark matter is not than what it is. We also know that dark matter doesn't interact with the electromagnetic force, meaning that it doesn't emit, absorb, or reflect light, hence the name dark matter, which adds to the difficulty of detecting it. In the universe, there is 6 times as much dark matter as there is normal matter. What about dark energy? Well, dark energy is related to the expansion of the universe. The analysis of the expansion rate of the universe suggests that gravity is not affecting the expansion. There is a mysterious energy at play here because the expansion is accelerating rather than slowing down. So we have dark energy. It is fascinating that our observable world and everything we know in it only adds up to about 5% of the total mass of the universe. So the universe is obviously far from being fully understood. But science relies on evidence, observation, and experiments, and it's certainly the best tool we have to understand the universe. And we should also be comfortable not knowing, because we would allow the possibility of exploration, and to me, there is beauty and mystery. Hope you guys enjoyed this video. Thanks a lot for watching.